Hey, sorry, everyone. I lost track of time. All right. How are y'all doing today? We good?
Doing good.
Good. Okay.
Doing good. How are you?
Been an okay day, I guess. Ready for the weekend.
Did you get your HEB order?
Yeah, I did. It turns out that if you're late, they'll keep it for the whole day, and then they'll put it back at the end of the day. So, all right. Well, so how did the homework go for substitution? Do you feel like you made progress, like mentally? You feel like you made some forward movement in terms of the expectation of the problems and the algebra and stuff?
Yes, sort of. The only problems I actually had problems with was the last four.
Okay.
So I was hoping you could go over them.
Hold on, let me see. This was 5.
5.5, 307, 306.
Okay, so you're talking about like number 36, well, 32 through 36. Is that what you're referring to?
Yeah, those were the most difficult.
Yeah.
Now the real question is: Are we getting problems like that on the test, or is it going to be more like the other 20 or 30 that we had?
Well, I mean, all of these types are fair game, you know, and in all honesty, I think when you look back on this section, you look back at these problems 34, 35, 36, when we look back on them in about 2 weeks, you won't think they're hard anymore.
Yeah.
Like you'll think that they're a lot easier. But on this test, I think that maybe one of those would be fair.
Okay.
I mean, I do want to make sure you can do basic substitution where, you know, the derivative's there and there's nothing fancy going on. But there should also be a problem where you have to kind of go at it, even though it's not obvious, and then make it happen, you know?
So would it be more like the cases where we have to, instead of solve for X, we'll have to see what U is equals to, and okay.
Yeah, yeah. So out of these problems, Cameron, I believe you asked about this. Is there one in particular you want me to go through, or you've already probably watched the video, so you probably know how they're done. Is there something you want me to do? You're muted, Cameron.
No, I didn't watch the videos.
Okay.
Because I was gonna save that for after class today.
Yeah, okay. Well, I mean, let's do one. Let's just warm up, okay? So
Okay.
you want to pick one?
I'll have to say this: the videos are well explained. They're very clear, and I found that very, very useful and helpful.
I use the video when I do my homework, and it helps a lot. You're like the first professor that does this, and it makes this easier, and makes much more sense.
Yeah, good. Yeah, it's kind of funny because my homework solution videos for my calculus sequence are probably the most watched videos that I have. Like, a lot of people don't watch the lectures, but I mean, I'm not talking like my students. I'm talking about other students that aren't even in my class will watch my homework videos.
Well, see, and the thing is that the approach you follow, you make it look all simple. Again, that might change my point of view once they see the test, but you made it look so easy. Oh, look, this is this, and it's.
Yeah. Well, I mean, I think that this stuff, it is easy if somebody's kind of leading you through it. You know, the hard part is you leading yourself through it. And that's where we're just trying to get better at that. You know, I mean, I was once you, right, sitting there, this was all brand new to me. So, you know, I had to develop that confidence that I could get through the problem, you know, and it just over and over. And I'll even say that when I was a Cal 2 student, I mean, I definitely wasn't as good at integration as I am now. I really got good when I became a tutor. When I started tutoring at the university is when I had to be forced to really understand it and do lots of problems. So,
And
okay.
as far as this, so as far as this substitution, I guess either practice or you have the eye where to tweak it and when, basically.
Yeah, yeah. And I mentioned that in the beginning of this class, that Cal 1 is very mechanical, right? Power rule, product rule, quotient rule, chain rule. It's something that you can teach someone and they can get it, you know, they get the pattern after a while. Integration is more intuitive. It's something where you look at it and you're like, I think I'm going to try this. You know what? I've done something like this before. I'm going to, but it's not like step 1, 2, 3, 4, right? It's, yeah. So Cameron, which one do you want me to do?
Let's say 34, because I feel like I was close on that one.
I had a feeling you were going to pick 34. All right, I am sharing my screen, right?
Yes.
Okay. All right, so I don't want to spend too much time on this because this is now kind of officially in the past now. So you might initially want to say, I'm going to choose u to be x cubed because the derivative of x cubed is 3x squared. And you do have an x squared. The problem is it's in the denominator and it's trapped under a root. So that's probably not, well, that's not going to work, right? Okay, so you don't really have much other choices other than just letting u be everything underneath the radical. And I don't want to include the radical because then when I take the derivative, it would get way too complicated. So I just take a derivative here, 2x dx. And then I ask myself, like, do I have 2x dx? And this is where things get a little weird. You have to realize that you could rewrite this. You have to see that you could rewrite that x cubed as x squared times x dx. So you're basically peeling off one factor of x and separating it. And that way the x dx matches that x dx. So you're only off by 2. So then you can rewrite this, or sorry, multiply both sides by 1/2. And that'll get you your x dx. That matches perfectly now. We also know that we're going to replace the x squared plus 1 with u. So there's one more piece that I need to resolve, and that's this x squared. I don't have anything for x squared yet, right?
Yes.
However, I kind of got lucky that this equation, I can solve it for x squared. If I solve that for x squared, I just subtract 1 on both sides. And now I have an equation for x squared. So I can replace everything in that integral with something that has u's in it. Does that make sense to everyone? Okay, so now I do that. Integral, let's see, I'm going to have a 1/2 that's going to pop out. The x squared up here becomes u minus 1. The bottom becomes square root of u, and then I have the x dx, which became the 1/2 du. I already pulled the 1/2 out. So that's where I am. And then once I'm here, because I have 2 terms in the numerator and 1 in the denominator, I'm going to split it into two fractions. U over, I'm going to go u to the 1/2 minus 1 over u to the 1/2. And the reason I switched it over to rational exponents instead of radicals is because I'm going to be using the power rule here in a minute. And so I'm just kind of getting everything set up. When I do this, just some algebra there, that's u to the positive 1/2. And then the other one, I'm going to bring the u up as negative 1/2.
Okay.
And now I can just do each one separately. So just interrupt me if there's something that I'm doing that you're not following here. Let's see, I add 1 to 1/2, that's 3/2. Reciprocal is going to be 2/3. And then, you know what? I'm gonna put this in brackets. Minus, let's see, 2 u to the 1/2 plus c. So that's just power rule on both of those. And I'm not showing the not showing the work. You might have to actually show that work. Like if you're not at that place where you're doing that in your head, that's okay. But I'm just trying to save us some time. And I'll distribute the 1/2 through. So I'll get 1/3 u. U is x squared plus 1 to the 3/2. And then I distribute the 1/2 through again. So minus 1 x squared, or yeah, x squared plus 1 to the 1/2 plus c. Here we go. You can leave it like that. You could change that to a square root and get rid of the 1/2. It's up to you. I'm fine with you just leaving it like that.
So I guess in this problem, the key is to realize when we have the x squared and solve for x squared, this way we'll have all the integral in terms of u. Is that correct?
Exactly. Exactly.
Okay.
Yeah, the part in green here we hadn't dealt with. Like everything else was going to be able to be switched over to something with u, but the green part didn't. But again, we kind of got lucky that this works. Just for your own information here, had that been x to the 4th up here instead, and then we peeled off and we would have been left with an x cubed here and an x out here, then it wouldn't have worked, because we would have been trying to solve for x cubed and we would have this, and we can't solve that for x cubed. So one little change to the problem and we're not able to do it. So this problem changing it to a 4 could not be done with u substitution. You would have to use some other method that we don't have yet. Okay, let me get into today's stuff. So I'm not quite ready to jump into 6.1. I want to get a couple of little things taken care of first. So this is going to be very helpful as we move on to be able to do some problems a little faster if we recognize a certain pattern that sometimes appears. So let's start with this. Let's say we want to do the antiderivative of cosine of x dx. Well, that shouldn't take you much thought. That should just be sine x plus c, right? We all just know that already. Okay, let's do this one. How about if we change the cosine x to cosine 5x dx? Well, the answer is not, okay? It is not just sine of 5x. Why is it not just sine of 5x? Why is it not that?
Chain rule?
Yeah, chain rule. If I took the derivative of this, what would the derivative of that be?
5 cos negative
Yeah,
cosine.
cosine of 5x times the derivative of what's inside, which would have been 5, right?
Mhm.
So the antiderivative can't just be sine of 5x. We'd have to do something to compensate for that 5 inside. So what could I add out to the front of this in order to wipe out that 5 when I do differentiate it? Am I making sense?
1/5?
1/5. We would need a 1/5 out here. Right? Let me do another one. I'm just trying to get you to see the pattern. Let's do cosine of negative 2x dx. The antiderivative of that should just be sine of negative 2x plus c. But again, because of chain rule, I know that a negative 2 would pop out, right? So I'm going to have to put in front of this 1 over negative 2. And that way, when I differentiate it and chain rule happens, the negative 2 comes out and this will wipe it out and it'll go away. Does that make sense?
Yes.
Okay, so maybe we can generalize this. What if we have antiderivative of cosine of a times x, where a is any constant? So a is a constant. I'm not telling you what it is. What would you do here? You would have sine of ax plus c, but what would you have to put out front?
1 over a?
1 over a. And that's almost the formula that I want you to kind of memorize. It's not, I guess it is a formula. it's an idea, and I'll tell you that idea after I do one more thing. Okay. So now I want everyone to see that what I have in here is a linear expression in X. In other words, X is the variable, A and B are just constants. All right. So think about what the antiderivative of this would be. We know it's sine of AX plus B plus C, but we have to scale it. What do we have to put out here? So think about what would happen when you differentiate the inside of that. What would pop out?
AX, I mean A.
Just A, right? It would still just be A. So you would just have to scale it by 1 over A again. Ah, shit, I'm not recording. No, I am recording. Am I recording?
Yes.
Yes, I am recording. Okay. All right. So that is the general idea here, is that let's say we have a linear expression inside of a function. Okay, so let me write it this way. I'm going to do this in different color because this is kind of the main idea. Let's say we have the integral of some function, and inside of it we have a linear expression. What we know is that the answer should be the antiderivative of that function evaluated at ax plus b, but we must scale it by 1 over a. Okay, so that's the key. We have a 1 over a that has to be there. So let's see if we can extend this into kind of a different problem. How about this one? Antiderivative of secant squared of negative pi x plus 1 dx. Okay, so when we look at this, we have composition, right? We have an outer function and an inner function. The outer function is secant squared. Do we know the antiderivative of secant squared?
10.
Tangent, right? So inside, we have a linear expression. Isn't that still ax plus b? See, a here is negative pi. Pi is a number, so even though it's a symbol, it's a number. So what I can tell you is that the antiderivative will be tangent of that linear expression plus c, but I must scale it out front by what?
Pi, 1 over negative pi.
1 over negative pi. 1 over negative pi. Do another one. Antiderivative of sine of 100x minus 4 dx. So again, you have an outer function, and then inside of it, you've got a linear function, or a linear expression. So do you know the antiderivative of sine?
Minus cosine?
Minus cosine. So I'm going to put here, watch what I do, minus, and I'm going to leave a little space, cosine of that linear expression plus c, but I have to scale it by what?
By 1 over x?
1 over 100.
100, sorry.
1 over 100. Now the negative is just out front, so it's like negative 1 over 100 times cosine of 100x minus 4. Are there any questions on this? Okay, this is going to come up again later, and we're going to be working through some problems, and we're going to get to this, and then I'm just going to go straight to the answer. And I just don't want everyone freaking out like, you know, how did that happen? All I'm doing is realizing I've got linear expressions inside, and I'm just scaling out the a every time. All right, here we go. 6.1, integration by parts. So we are starting this section. I know that's hard to reach. Do I need to make that a little bigger for you? I'm going to go through these notes, so you don't need to worry too much if you can't see it at this point. In fact, let's just get rid of it because it's just a distraction. Okay, oops. Okay, so here's the idea. Right now, if we try and take an antiderivative, okay, and we have, let's say, x times sine x dx. Right now, there's nothing we can do to do this problem. And the reason we can't do it is because we can't split this up. There's a product in between, right? There's a product there. And there's not a rule that says that we can just do the antiderivative of each one, right? Like this right here is a big mistake, right? To do this on the test, right? Do you see what that student did? Just took the antiderivative of each one, right? Individually, and just added a plus c. That is not correct. Okay, and I've said this for a while. If we have multiplication between two things, you cannot just take the antiderivative of each one separately. So this is a no-go. So right now we have no way of doing this. So I want you to look at it. I want you to look at it this way. What we have in this form, this right here is some function of x. And we'll call it f. Okay, and then this function right here is g, right? And we have a product in between them. So right now what we're trying to figure out is can we come up with some sort of formula that might help us do this, right? Maybe there's a formula. Well, there turns out that there is, but there's a catch to it, okay? So I'm going to take you back to Cal 1, and I'm going to talk about the product rule from Cal 1. So the product rule in Cal 1 says that if I have f times g, and I want to take the derivative, that it should be the derivative of f times g plus the derivative of g times f, right? We agree with this?
Yes.
Okay, now, what I'm going to do next is very interesting. I'm going to now take the antiderivative on both sides of this equation, all right? Now, what does the left-hand side become? We're taking the antiderivative of the derivative. So what should happen? So you start with f times g, right? You take its derivative, and then you take its antiderivative. So it should just end up being back to f times g, right?
Yes.
So this is just f times g. And then on the right-hand side, what I'm going to do is I'm going to use the fact that there's an addition symbol here, and I'm going to split this into two integrals. I'm allowed to do that because we've already said that when you have integration or differentiation, if you have pluses or minuses, you're allowed to split it into two. So are y'all okay with this so far? Understand what I've done algebraically?
Yes, sir.
Okay, now what I'm going to do is something weird. I'm going to just take this right here, and I'm going to move it to the left side of the equation. Now, to move it means I need to subtract it from both sides. Okay, so I'm about to sit here and subtract this integral on both sides. I don't know what that integral is, okay? I don't know what the answer is, but I'm subtracting it on both sides. So what I have now is this, f times g minus the integral of f prime times g equals the integral of g prime times f, and I'm going to write it like that instead. I'm just changing, instead of g prime f, I'm going f g prime. It's multiplication, so I can split it. Okay? Is that all right, everyone? That's just algebra. And now, next step, I'm just going to rewrite it one more time. I'm actually going to make the left side the right side and the right side the left side. So I'm just switching their positions. And you're allowed to do that. Anytime you have an equation, it doesn't matter if you write, you know, if I say x equals 4, it's the same as saying that 4 equals x. So it doesn't matter which side it's on. So that's it right there. Okay, so look at this. I want you to just look at this for a second. What this is saying to us is this. And this is the way I want you to interpret this. let's say, does everyone understand so far where we are? Any questions on how we got here? Okay, so let's just kind of take a deep breath and just look at this. Let's say we have an integral, okay? And let's say that in that integral, we have some function f sitting there looking at us, right? Like up here, maybe it was, and I'm gonna erase this here. So maybe in this integral, maybe the x is like the f, okay? And then next to it, we have the derivative of g. So you have an integral, you have a product. The first part of the product is some function. The second part of the product, which is the blue part, is the derivative of a function. Not the derivative of f, the derivative of some other function. So let's go back up and look at this problem up here. Could everyone look at this and say, hey, look, this we could call f, yes?
Mhm.
Now, the question is what's left here, is sine x dx the derivative of something? Yes, it is, right?
Yes.
It's the
Negative
derivative of what?
Negative cosine.
Negative cosine. So I could see that that is the g prime of, like, that is the derivative of something, right? Yeah? Okay, well, what does the formula tell us? If you have,
I have a question.
yes,
So if you go up, you see that there's dx right there. So we'll include the dx in part of the g function and call
Yes.
it negative cosine.
yes, yes. Well, we are including the dx because we're saying that this part in blue is the derivative of something. And so it'll have that little differential, that little dx will be there. Remember when we were doing substitution, we let u be whatever, and then we took derivative on both sides and we put the dx on the right side? That's the same
Yes.
thing we're doing here.
Okay.
Okay, so if we start with an integral and we see a function and multiplied next to it is the derivative of some other function, then according to this equation, the answer to that integral is f. Okay, do we know what f is?
Yep.
Yeah, we know what f is. Okay, now do we know what g is? Well, g is the antiderivative of g prime, isn't it? So like back up here, if this is g prime, what did we say g would have to be then?
Cosine x.
Negative cosine of x, right? So this part right here, we should be able to get. If we can find the antiderivative of this g prime, then we should be able to figure out what g is, right? And then minus, now here's the catch. Now you have a new integral, okay? And your new integral, right? This new integral, do you see what's in the new integral? It's not f anymore, it's what?
F prime.
F prime. Do we know the derivative of f prime? Well, I mean, if we're given f, can't we find f prime? Just take derivative?
Mhm.
Okay. And how about g? Do we know what g is? Well, we had to know it for this step, right? So we should know g. Now, I know that this looks really weird, all right? But this is a super, super important formula. And this is what we refer to as integration by parts. Now, I want to continue to talk about this before we actually do an example, all right? What I'm going to do is I'm going to kind of start over, and I'm going to use different notation. And you'll see why I'm using different notation in a moment. Okay, so let's say that we had originally we were trying to find the antiderivative of f times g, right? dx, that's what we were trying to do. And what I did is I said, let's look at the product rule. And I took the derivative, didn't I? So what I want us to do instead of this is let's call this u and let's call this v. So instead of f and g, I'm going to use u and v. All right? Is that okay with you? Yeah? So if I want to know from Cal 1 what the product rule is, it would be u prime times v plus v prime times u. And then if I integrate both sides, I'm going to get u times v equals integral u prime times v plus integral v prime times u. And then what I'm going to do is I'm going to move this piece over to the left. So I'm going kind of fast because we just did this exact same thing with f and g, right? I'm going to write this a little bit different. I'm going to change the order on these two. I'm going to swap the order. You'll see why in a second. Equals, and I'm change the order on this one. And last step, I'm going to make the left side the right and the right side the left. Okay, so that is the exact same, me going through everything that we just did a second ago, just swapping f and g. So are we good? Okay. Now I'm going to do something a little, just slightly different. I'm just going to see where we have v prime here and we have u prime. I'm just going to use a slightly different notation. I'm going to write this. U dv, instead of writing v prime, I'm going to put dv for like the derivative of v, equals u times v minus integral v times, and instead of using u prime, I'm going to put du. Okay. This is the formula that you want to know. This is the one that you want to memorize. All right. So there's a little cute little saying that you can remember to help you memorize this. And the saying is ultraviolet minus voodoo. I think is that voodoo? Is that spelled right? V-O-O-D-O-O?
There's multiple ways to spell it. It's fine.
What's that?
There's multiple ways to spell it. It's fine.
Oh, okay. All right. So ultraviolet minus voodoo. All right. So ultra U violet minus, now you have to remember the integral part. Okay. That's not in the saying. Minus V du, voodoo. Got it? Voodoo, voodoo. Are we good?
Yeah.
That was taught to me. It's not my, this is not my thing. Okay. But it sticks, I promise you. You'll never forget ultraviolet minus voodoo. It just automatically sticks, all right? Okay. Let's do that first problem. Let's see if we can do that first problem. And let's use this formula and see how it goes. I'm gonna get rid of all these arrows. Okay, so the first problem we had, integral x sine x dx. So when we look at this, we have to first realize there's nothing we can do. Even basic U substitution, that the section 5.5 that we just finished, there's no substitution you can do here. You can sit here all day long and try substitution. It's not going to work. Okay? So what you need to do at this point is you need to realize that, well, integration by parts is possible. You have two things here. You have an x and you have a sine x, right? Those are the two things being multiplied. And in the formula, it's saying that you have a function, the integral of a function u times the derivative of something. And we just said a second ago that we could choose this one to be the u, and then the x including the dx, or the sine x including the dx, that could be our dv. Do y'all see that?
Mm-hmm.
Okay, that's one way you could do it. Or you could have done this. You could have rearranged it and made the sine x go first, and then the x dx by itself, and then call this part your u, and this part your dv. Does everyone see that you could do this problem in two different ways? On one hand, we pick the u to be x and the dv to be sine x dx. On the other one, we let the u be the sine x and we let the dv be the x dx. Do y'all see the two different ways? Yes? Okay, one
So,
way
sir,
works.
you're showing us this to show that like we could do it both ways and it doesn't
No.
matter?
No, I'm showing you this because only one way works. And,
Oh, okay.
and what's going to guide you is what I'm about to try and explain to you. And that is, what is the essence of the integration by parts, okay? So let's go back up to this and let's take a look at this. Okay, if whatever we choose to be our u, right? Whatever our u is, and we had two choices here. We could have gone with x or we could have had sine x. I want you to think about what that becomes in the new integral, because at the end of the day, we still have to do integration, don't we? Like the formula still has an integral in it. But think about what would be in here. So we pick u to be something. What's in the new integral? Is u there? Is u in the new integral or not?
Yes, it is.
Exactly u?
du.
The derivative of it's there, right? So what's happening is that the original integral had u in it, right? The original integral had u. But the new integral has what? The derivative, right, of u? Okay, what about the dv? Over here, the dv, in the original integral, it's the derivative of something, right? So in the two cases we have here, it could have been the sine x dx or it could have been the x dx, right? We had two choices there. In the new integral, what is it? Is it dv? Is it the derivative?
Is the integral.
No, it's the antiderivative, right? Okay, I still get goosebumps when I talk about this because I can remember Dr. Richardson telling me when I was learning this that the integration by parts is a formula that allows you to transfer the derivative from one function to the other. That's what's happening here. In the first integral, you're looking at u. In the new integral, you're looking at the derivative of u. On the other hand, in the original integral, you're starting with the derivative of a function, and in the new integral, it's the antiderivative of that function. Okay? So when you're looking at these two cases that we could have done, which one seems like would be better?
Or easier.
The first one?
Okay, so why would choosing that x to be u be smart?
Because it would just multiply by 1.
Because in the new integral, it's 1, right? In the new integral, it's going to become 1. Yes? Okay, and then the green part, the sine x dx, that in the new integral is going to be what?
Negative cos.
Negative cosine x. So without writing anything down, what is inside the new integral?
Negative cos. dx.
Negative cos times 1, right? Can you handle that integral? That's just cosine x, right?
Yeah.
We should be able to do that. Do y'all see that? I mean, I'm asking you if you see it in your mind. Okay, let's compare that to the other way. What if we did this way? Okay, so we choose our sine x to be our u. What's it going to be in the new integral?
X squared?
No,
Cosine.
the u. We chose our sine x to be the u.
Cosine x.
In the new integral, it's going to be cosine x, right? So imagine this new integral that has cosine x sitting in it. But then we're forced to make that the dv. So in the new integral, what's going to be in the new integral? That dv is going to have to turn into v, isn't it? The antiderivative. What's the antiderivative of x dx?
Dx squared.
No. Antiderivative
One
of
half
x,
x squared.
Yeah.
1/2 x squared. So think about this. If we start here, the new integral is going to have some crap in front of it, and then it's going to be a new integral. It's going to have a negative, it's going to have a cosine x in it, and it's going to have a 1/2 x squared in it. You understand? That's more complicated than what we started with. We started with x sine x, and if we do it this way, we're going to wind up with cosine x times 1/2 x squared. Whereas if we do it this way, in the new integral, we said that we're going to have a 1, and we're going to have a negative cosine x. And I'd rather do that one than the other. Okay. This is just to get us, our brains working, trying to understand this whole idea of transferring the derivative. Let's start a new page. Let's do the problem.
So in this one, if we choose the wrong option, we should be going in loops, right? Or how does that work?
I'm going to do the problem the right way, and then I'm going to do it the wrong way. And I think after I do it the wrong way, you'll see how I know I'm doing it the wrong way.
Okay.
Okay. And let me put the formula up here. It's u dv equals u times v minus integral voodoo v du. Oh, by the way, this formula is on your formula sheets. It is the very first one. It's the very first formula. Okay. Okay, so is everyone clear with the idea that when you're doing integration by parts, you have to pick something to be your u and something to be your dv? Yes?
Yep.
Okay, so the way that I do these problems, and you'll see me doing this the rest of the way we do integration by parts, I draw a table off to the side. I always put u here, and I put dv down in the bottom right-hand corner. That's the way I do it. People do it different ways. It's the way I've always done it, all right? So now I get to make a choice. And let's go ahead and make the choice that we're going to let the x be the u, and that means everything else is the dv. So I have to put sine x dx here. Now, in the new integral, I need the derivative of u, don't I?
Yeah.
And I also need the antiderivative of v. So let's do those. So what I'm going to do is over here on this table, anytime I go down, I'm going to differentiate. Anytime I go up, I'm going to integrate. So I'm going to go and write du equals, and then what is the derivative of x?
1.
1, but I'm going to write 1 dx. 1 dx. And the reason why is because I'm taking derivative of u with respect to x, which would be 1, and then I'm multiplying both sides by dx. All right, now on this one over here, let's integrate up. So that would give us v, wouldn't it?
Mm-hmm.
The antiderivative of sine of x dx. So you can almost imagine like a little integral sign here. Integral, we're going up, right? And that's giving us what?
Cosine x?
Negative cosine x, right?
Yeah.
So dv equals sine x. So we get negative cosine x. Now, technically, aren't we supposed to put plus c? Right? But I'm going to just wait till the very end of the problem. I'm going to put plus c. All right? And that'll take care of the constant. Any questions on this little table I made? You all ready to put it together? This is equal to, and now let's just read this formula from left to right. U. So U in our table is this, right? X. So I'm just going to write X times now V. V in our table is the top right, which is negative cosine X. So I'm going to put the negative in front of the X and put cosine X here. Is that clear where that came from? That's just U times V. So really to do this part, to get this part, I'm just doing straight across. Those two multiply together, right? That's what I did. And then I have to remember minus integral. And now I need voodoo, right? V times du. And V times du is this times this. It's like diagonally. You're going to just multiply those two together. And when I multiply those two together, all I get is negative cosine x dx. Notice the dx came from there, right? We're almost there. Negative x cosine x plus integral cosine x dx. All I did there was pull the negative out of that integral. The two negatives become plus. And now I'm very happy to see this. Antiderivative cosine x, I know what that is, right? That's just sine x. Plus sine x plus c. There it is. Shit, we're halfway through class. We've done one problem. Yeah, we have to build up. Okay, yes? Okay, let's check. Is that the antiderivative? Let's just take derivative real quick. So I'm gonna go fast here. Taking the derivative of this, I have a product rule right there. So I have to do derivative of the first one times the second one, plus the derivative of the second one times the first one. Okay, I'm done with product rule, plus the derivative of sine x, which is cosine x. Okay, this is negative cosine x, and then I get two negatives there, become plus, so plus x sine x, and then plus cosine x, and the cosine x's cancel, and you get x sine x, which was the original integral, right? So it worked. It's pretty awesome. Now, what would have happened had we done the problem and we chose the wrong u and dv? So if I would have come over here and I would have done u here and dv here, and I choose u to be the sine x and my dv to be the x dx. Let's say I would have done that. At this point, I don't know I've done anything wrong, okay? But as I go and try and generate this table and I differentiate down here, I get cosine x dx. And when I integrate up here, I get 1/2 x squared, right? Antiderivative of x is 1/2 x squared. At this point, this is where red flags would start going off, I guess. Red flags go off. Do red flags go off? I don't think red flags go up, right? And the reason why is because I'm already thinking about voodoo. I'm thinking about that new integral. And do you see that that new integral is not something nice? It's actually more complicated. It's worse than what we started with, right? We started with a single x in front of sine. And in the new integral, we're going to have 1/2 x squared in front of cosine. And that just doesn't seem like it's gotten any better, right? So at this point, I would just ditch this. But it's not one of these things where it should be like a 50-50 coin toss. Like you should be thinking about what's going to work before you actually do it. Like what gets better when you take its derivative in the new integral? All right, let's do another problem. Okay, arc sine of pi x. Y'all think about it. I want y'all to put a little table on the side and think about what would be u and what would be dv. I need a refill. Be right back. Y'all can think about that. Does anybody see what's different about this problem compared to the one we just did?
Yeah, I guess U is not, U is 1.
I think it's like the product rule is inside the inverse sign. That's the difference.
Okay, so like in the previous problem, we had x times sine x, right? X times sine x. So it was very easy to see we had two things being multiplied together, which is the only time you can use integration by parts. Here, do you have two things multiplied together? Well, you do, but you just have to kind of squint your eyes a little bit. This is actually 1 times dx. So you have two choices here. You can put arc sine of pi x there and put a 1 dx here, or the other way around. You could put, let me put the table below, just show us our two options. So I could put arc sine, I'll do the arc sine up here. I could do arc sine of pi x here, and that would force me to put the 1 dx here. Or I could put the 1 here and put the arc sine of pi x dx there. Do y'all see that those are our two choices?
Mm-hmm.
Okay, which one is better, the top one or the bottom one? And why?
I
think
would
the
say that
bottom.
it's the bottom one,
Okay, why?
because we should always look for U to be the simplest of the two. I don't want to say numbers, but the two, whatever the
Yeah, so it's almost like you want your u to get better in the new integral, right?
Yeah.
And so when you take its derivative, we know the derivative of this would be just what?
0, the x.
0. Okay, that's weird. Now what about this part? You have to go up.
So that'll be 1 over pi.
You're taking the derivative.
Oh.
We want the antiderivative, right? Because we're trying to get back up to v.
Is the top one the right one?
Yeah, see, look, this bottom one, this step right here, you're trying to find the antiderivative of that? That's the original problem. Right? Which we don't know the answer. So even though it looked like this 1 becoming better here would be good, the fact we can't go up here means we have to do it the other way. Okay? So, Abe, you had just looked it up on your table though.
Mhm.
If we're going to do it this way, we have to differentiate down. So what is the derivative of arc sine of pi x? So you start to say 1 over
1 over a square root of 1 minus x squared.
yes, and for us it'll be pi x squared, right?
Mhm.
And then chain rule times pi dx. Is everyone good with that? You can see now why we covered derivatives of inverse trig functions earlier. Okay, so we've got that derivative down. Now we have to integrate this up. We've got to go up to v. The antiderivative of 1 with respect to x would just be x.
Okay.
Now, when you're thinking about voodoo here, think about what's in blue. You've got to multiply those together, right? And then you've got to integrate that. And you might look at that initially and be like, shit, that's going to suck, right? You may not say shit. I would say shit. But, I mean, doesn't that look bad? Doesn't that in blue look bad? Okay, let's not freak out, though. That's the only choice we have. This bottom one doesn't work. So we just have to keep going. And let's just see where we get, okay? Are there any questions on this setup so far? Off the derivative or the table or anything I've done? No? Okay, here we go. This should be equal to the formula ultraviolet, right, which is straight across the top first. So that should be x times sine inverse of pi x. Notice I'm not calling on anyone today. I'm only doing that because of time, and you just need to stop me if you don't get something, okay? So that's ultraviolet minus integral, and then I need the voodoo, which is the blue stuff multiplied together. So I'm gonna write x times 1 over square root of 1 minus pi x squared times pi also dx. Yeah, so that integral, when you look at it initially, you look at it and you kind of freak out a little bit. Does anyone see it though? Does anyone see what you can do with that?
Yeah, the integral
You
should
sub?
be,
Can we multiply the x in and then do u sub?
What do you mean multiply the x?
Like, can't we?
I think you're correct. You're just having trouble saying what you're wanting to do. Maybe.
Yeah, just like simplify it into one big fraction.
Okay, so here's what I've done first. I put the x and the pi together up top. I also decided to go ahead and square the pi x. So it's squared the pi and the x. And that's what we have.
mhm.
And now you look at that, and again, you're freaking out, but then you just say, wait a minute, we just finished 5.5, which was basic U substitution. You start asking, do I see something in its derivative? Do I see something?
You take the whole thing is just negative or sine inverse, right?
Not
No,
quite.
just-
Not
just
quite. Because of
let
the
that-
x up top. Because the x up top, it won't work.
Let that equal the u and then take the
But-
derivative.
Yeah, so at this point, this integral right here, I'm about to do U substitution on. So I'm going to let U be everything underneath that root. Now, the reason why I'm doing that is because I know that the derivative of this, right? The derivative of 1 is 0. Pi squared is a constant. So when I take the derivative of this here, the 2 pops out. I have a negative 2 pi squared x dx. You need to be comfortable with the idea that the derivative of this whole thing is this. Does everyone see that? Sure. Now, do we have that? Like we are trying to replace this x pi x dx, right, with something. Do we have it? I have an x dx. I've got too much stuff in front of it, right? I have a negative 2 and a pi squared. What can I do?
Multiply by 1 over negative 2 pi.
Excellent, perfect. If you multiply the left side by 1 over negative 2 pi, if you do that on both sides, you will be left with a pi x dx on the right side. So from this step to this step on both sides of the equation, I think that was Cameron, suggested we multiply by 1 over negative 2 pi. And what that did is it killed off one of these pi's and it killed off the negative 2 and left us with a pi. And that's exactly matching now, right? Exactly matches what we wanted there.
So why are we substituting values? Because I remember in the previous question, we didn't substitute values.
Welcome to integration by parts. So in the first problem, it just worked out, right? Everything was great.
Mhm.
Now in the second problem, I'm showing you that you could do an integration by parts problem where when you get that new integral, it might require you to do a different technique. Like you might have to do U substitution on that integral. So this goes back to what I said before, like each section is going to build on itself, right? Does that kind of answer your question? Like they're not all going to look like the first example. It's gonna get messier too. Like it's about to get messier. So I'm not going to try and sugarcoat it for you. all right? Just, if you have questions, this is when you need to be asking. All right, so here's what I'm gonna do. I'm gonna go over here and I'm gonna do this as like scratch work on the side, okay? Because really what I'm doing is I'm trying to figure out what this integral is right here. I'm trying to figure out what this is, right? So let's just do that all over here. All right, so that new integral becomes, so let's do the substitution. What's the blue gonna turn into? What's the pi x dx gonna become?
du.
Du with that 1 over negative 2 pi, right?
Mhm.
So I'm gonna put the 1 over negative 2 pi out here, slap the du on the back. Okay, what's still there though? What about that green part? I'm gonna replace the green part with what?
U to the negative half.
Yep, okay, so that's gonna turn out to be 1 over the square root of u, right? 1 over the square root of u. That's what was still there. And that can be rewritten as 1 over negative 2 pi integral u to the negative 1/2. Who said that? Was that Minato or CJ? Okay, good. So that'll turn into that. Now we know the antiderivative of that, don't we?
Yeah.
Antiderivative of that is 1 over negative 2 pi times, okay, we add 1 and then 1 over that, it's 2u to the half plus constant. And now I clean that up a little bit. These 2's cancel, oh, sorry, the 2's cancel, the negative does not. And so I should just have negative 1 over pi square root of u, and u was 1 minus pi squared x squared. See, yeah, we're starting to do grown-up math now, okay? There's a lot going on here. That is the answer to the red box, right? So we're ready for our final answer to the problem. Are there any questions up to that point?
Are you not going to include the plus C in the final answer?
I am at the very end. I put it here. I'm going to just throw it in at the end.
Okay.
You know, we just want to not forget that it's there. Okay. So x arc sine of pi x. Okay, and then I had this minus sign, right? That minus right there. But then I had a minus here also.
So it become
Those
positive?
together it'd be plus, right? So plus 1 over pi square root of 1 minus pi squared x squared plus c. Sorry if that was loud.
Oh my gosh.
There it is. That is the antiderivative of arc sine of pi x.
That's
We could
not-
check it. Are we checking it?
We could, but it's gonna take forever.
Nah, it won't take long. I'll do it fast. Okay, so here we go. I'm going to stop checking at some point. Here's product rule right there. Product rule derivative, that's 1 times arc sine of pi x plus now the derivative of arc sine of pi x, which is 1 over square root of 1 minus pi x, that's squared, and then times chain rule derivative of what's inside, which is pi. Finish the product rule, so you need the x there. Okay, that takes care of the product rule. Plus 1 over pi. Okay, that's just a constant, comes for the ride. Derivative of the square root of something is 1 over 2 times the square root of that something. I'm going to rewrite that as pi x squared, doesn't matter. And then times, I need the derivative of what's inside here with respect to x, which is going to be negative, I'm out of room,
Negative 2 pi square.
2 pi squared x. And I'm done. So this should just clean up. Let's see, the 2's gone, 2's gone, one of those pi's is gone, one of those pi's is gone. Let's see, yeah. Holy crap, man. Do y'all see this? Are y'all still there? I don't know what just happened. Okay, this is arc sine of pi x plus this together. I'm gonna put the x, pi x on top. over the square root of all that crap, right? And then look at this one right here. Do you see that minus sign? It's going to become minus, and what's on top?
X,
X times
pi.
pi. We still have a pi, right? Pi x over
Yeah.
the square root of that same junk, right?
Mm-hmm.
These two are exactly the same, just opposite in sign. That's like plus an apple minus an apple. Your answer is arcsine of pi x. All right. The fun keeps coming. So a couple of things changing here. I'm going to use the variable t instead of x. How do you know that the variable is t?
Because dt, it's at
dt.
the end.
Yep, dt. Okay, so the dt is telling us the variable is t. Now what's that thing I put in front of the t? What the hell is that?
Constant, beta.
Constant. It's beta, okay? Beta is like alpha or A or B or C. It's a number, we don't know what it is, but it's a constant, it's not a variable. All right? So I'm not sure that I said this in the beginning of the semester. If I did, I apologize, but I'm gonna, if I'm repeating myself. But, are you going? Okay, be careful. This Cal 2 is a journey, and I've been teaching this for a long time, long time. And I don't ever get bored teaching this class because I enjoy watching the journey that you all are taking, because this is not easy. Okay, so this stuff it's just going to continue to test your patience and persistence, right? But at the end, I think we're all going to be better off, for the journey that we're going on here. So I'm super excited to see how you react to what this one's going to require. So what are you thinking? Can we
U could be t squared.
make u t squared? Yeah.
Or no.
Yeah.
The other way.
Your other option is to make u sine beta t, right?
Yeah. Let's do that.
So I'll put them both down side by side, and we'll just kind of see which one looks better. If we let u be t squared, then the derivative of that is 2t dt. That forces us to have used the sine beta t dt as the dv. And what would be the antiderivative here? Be careful. What would be the antiderivative there?
It'll be
Negative cosine.
Negative cosine
BT
beta t.
Times b.
and with b multiplied by b.
Close. It's the
1 over
antiderivative.
b.
1 over beta, yes. So I'm going to add out here negative 1 over beta. Okay? That's what we started class with. Remember I said if you have a linear expression inside, you always have to scale by it. Here we had beta t inside, so we have to put a 1 over beta on the outside when we take the antiderivative. I said that would come up again. It just did. Okay, now look at voodoo. Look at voodoo. That and that. Let's just continue with this one, and then we'll talk about the other option we could have done. Okay, can we do that? Let's just continue with this one. Do you like this new integral? I mean, I'm going to write it down. First we have to do the ultraviolet, which is across the top. It's going to be pretty ugly, but let me try it. Negative 1 over beta t squared cosine of beta t. Now I kind of rearranged the order of things there. Like I didn't put the t squared first because I know that negative 1 over beta is a constant, so I put it in front of the t squared. But that's just ultraviolet. minus, and I'm going to leave a space here, okay? I'm going to leave a space there, minus voodoo. Voodoo is this. What constants can come out of that integral? So what in that voodoo is a constant?
1 over beta.
1 over beta. What about the du?
Negative
T.
2 over b.
There's a 2, right? There's a 2 in that du. So what would I do here? I'm going to put negative 2 over beta.
Okay.
Okay, so what I did is I took the, let me see, I took the 2 here and I took the negative 1 over beta. Those are all constants and I pulled those out of the integral just to make my life easier. That make sense?
Yes.
Okay, so what's still in the integral?
Cosine beta t.
Times
dt.
dt.
t dt, right? So I'm going to write it this way, t times cosine beta t dt. I just decided to put the t out in front of the cosine. Okay. I'm going to call on somebody. Is Alejandro here? How about Sumit? Sumit? So Sumit is here every day, but is never here when I call on them.
I think he works during this time. He had his camera on the other day, and it looked like he was actually in the middle of work. And he was trying to multitask.
Oh, really? Okay. All right. Well, maybe, maybe not. Okay. How about Brian Vasquez? Brian?
I'm here, sir.
Okay, there you are, Brian. So, Brian, we started out with the original integral, and we turned it into this new thing with this new integral. Have things gotten better, Brian?
No.
Like effectively, what have we done, Brian? Like all that work, and what have we accomplished?
Looks like we've gone backwards.
Okay, so the sine beta t turned into a cosine beta t, right? So that really didn't change much, right? Sine went to cosine. What happened to the t squared? What did it become in the new integral?
T.
T, right? So it's not as complicated now, right? Because it's a t, not a t squared. And the reason why the t squared became a t is because we chose that to be the u, and so we know that the derivative of that would bring the power down by 1, yes? But it's still a problem, right? Do you agree that t being out front is still a problem?
Yeah, that's
So
the same.
What could we do? What could we do to make it not be a problem?
Do the same again?
Do it again. Why don't we do integration by parts again? But do it on this integral. So we're gonna do integration by parts a second time. And when we do it this second time, if we choose the u to be t, this time around the t is gonna go away, isn't it?
Yeah.
Yeah.
It'll
So
be
this is an example of integration by parts having to be performed 2 times within the same problem. All right, so we are now working, this is our new little universe, okay? This is our universe. We are working in that universe only right now. And we're gonna start a new integration by parts table. We're gonna choose u to be t. dv then has to be the cosine beta t. dt. Brian, does that make sense?
Yes, sir. Is it because it's being multiplied?
The reason why we can't just find the antiderivative of this like easily is because it's t times cosine beta t. So we can't just do them separately, unfortunately, right?
So in a perfect world, would it only take one table if the derivative was like cosine or like whatever it was times 1? Is that like the perfect world?
Would it only take one? I'm not quite sure what you're saying.
In the previous problems, it was always like the one, like it's just multiplied by 1, like cosine times 1 or something else times 1.
like this.
Yeah.
So this was like X. So when we did integration by parts that one time, we basically eliminated that X and made it turn into a 1, right?
Yes.
So we only have to do integration by parts one time.
So I guess what he's saying, if we have, say, an X cubed, do we need to do that 3 times in cases like this?
3 times.
Okay.
Yeah. And if it's X to the 4th, 4
4
times.
times.
Yeah. I wouldn't do
And we
that.
should be taking the same U in all cases, in all 3 cases or 4 cases.
Well, yeah, because what's happening is each time you're doing it, it's
You're
getting
degrade-
better. It's getting better and better and better, right? So if you start at t cubed, and the new integral will be t squared, and the new integral will be t, and then the last integral, it would be 1, right? So you just keep chopping away at the power. Does that make sense?
Because as far as the other side is going to be repetitive, it's always going to be the same. Cosine, sines, cosine, sine.
That's right.
Okay.
So yeah, the dv part just keeps flipping back and forth between sine and cosine. But the power, the t to the power is the one that you just kind of like chipping away at it.
Unless we have a case like this where it's just beta, then we'll have 1 over beta square, I guess, right?
Yeah,
If
we're going to keep on getting betas in here. Let's finish this out because we're close. So
as long as we don't have one of those in the test, I guess.
are we not going to?
No. I mean, 3 steps.
I wouldn't
3
do
different-
3. I don't think
Okay.
I do. No, I don't think I've ever given one with 3.
Okay.
Yeah. But you should definitely be able to do integration by parts more than one time. Yeah, like within the same problem. Okay, so the antiderivative here is 1 over beta sine beta t. So I made my table. T was the u, dv was the cosine beta t dt. I went down and up on that table. And now we've got to be super careful here, okay? Watch this. We have negative 1 over beta t squared cosine. Well, shit, you know what? Let's not do all that yet. Let's just continue. I told you we were in this universe over here. Let's stay in this universe. So according to the formula, this should be ultraviolet, U times V. Okay, that was me multiplying across the top. And now minus the integral of voodoo. So minus the integral of voodoo. And do you see that I've now started to leave a space here after the minus? And that's because I want to pull constants out anytime I can. So when I do my voodoo, which is across this way, the only constant I have is 1 over beta. And what is still in the integral?
So that would be V. That's 1 over beta sine beta t.
And then dt, right? That comes from the du, voodoo.
Yep.
All right, now we look at this new integral, right? Now we have a new integral. Can we do that integral?
Sure.
Okay. Finally, we've gotten it that we don't have a t out front anymore that's causing issues.
So what happens to the old integral? So like we get rid of them as soon as we get it more simplified?
No, we're going to add them.
Yeah, we're going to put these together.
Oh,
We're gonna put
okay.
these together. This is 1 over beta minus 1 over beta. Okay, now what's in that black box? The antiderivative of sine of beta t is negative 1 over beta cosine beta t plus c. You okay with that? That's this piece right here is the antiderivative of that. One more cleanup before I put it all together. 1 over beta t sine beta t plus 1 over beta squared cosine of beta t plus c. All I did there is put the 1 over beta together to become 1 over beta squared. The minus minus became plus. All right. Now I'm ready to come back over here to the left side. and put it all together in a final answer, right? So this piece right here, I started to write down. Now, we have a minus minus there, right? That's going to become plus. Plus 2 over beta. Now, this purple box is that, right? That's what that purple box became. So that 2 over beta that's out front must get distributed through to everything we have here. I'll bring in the plus C at the end. Okay, so this is that. This is that. And then the purples were here, right? Is that too much color for you? Final answer. -1 over beta t squared cosine of beta t. I'm going to distribute the 2 over beta through. Plus 2 over beta squared t sine of beta t plus 2 over beta cubed cosine of beta t plus c. All right, we're starting to do some Cal 2 now. Like this is starting to feel like Cal 2. All the algebra, all the stuff you got to keep track of. This is what makes people like feel like they're suffering. What do y'all think? I mean,
so like in this question, we never did a substitution. So how would I know if I would have to do a substitution or just integration by parts?
Yeah, that's a great question. That's what you're going to have to figure out, right? You're going to have to, every integral, when you see it, you're going to have that intuition as to what to do. Like in the previous problem, when we got to this one right here in the yellow box, when we got to that, I asked, how are we going to do that? And somebody said substitution. Who said that? Someone had mentioned it. I was looking down. Okay, so Minato, why did you know to do substitution there?
It looked very similar to the problems that we did previously, and the denominator, the pi squared x squared, going like accordingly to the numerator, having both the pi and the x, kind of reminded me that if the denominator can be substituted into u, then it would work out.
Yeah.
Numerator.
Yeah. So like I can explain why I knew to do it. And all I can say is because I've done thousands and thousands of integrals. But for a student who's just getting exposed to this, it's hard for me to say what triggers that. I think Minato did a really good job just now explaining why, like how he thought that. But practice, right? It seems like Minato's done enough problems to have this recognition. It's hard to teach that. Like I can show you, like this, I can show you all this. It's hard to teach the intuition. That comes with the practice. It really does.
So would you say that at the result, once I say call it u, it's degrading in 1 degree, t squared then t and then 1, but also we can say that beta is actually increasing. It was to the 1 and then square and then cube.
Yeah, so you would think that if maybe the original problem would have been like t cubed, we would probably expect in our answer to see a beta to the 4th, right? Because we would have had to do it one more time. That seems reasonable. That seems reasonable. But how do I say this? We're not, there's no way for me to just put like a cookie cutter like, here, this is what you do every time you see this. You know, like, I know, Abe, that's not what you were saying, and Mufasa, you're not saying that either. But if you're looking for like easy patterns with integration, there's really not easy patterns. There's nothing that you can just always latch on to and say, when I see this, I will do this. It again comes with the exposure. Like, for example, what you've learned in this particular problem is that with that t squared out there, and with the fact that there's a sign next to it, each iteration of integration by parts, we knock the power on t down, right?
Mm-hmm.
And what was good was that the sign just kept on switching back and forth between sine and cosine, right? Everything was good there. We never had any problems going up on the table, right? Because it was just a sine or a cosine. And as we did it each time, the t came down. Look at the next problem though. It just totally fucks with your head, you know? Like, it's like just when you think you've got some latched onto something, then you get something like this. E to the 2, let's go back to x. I'll put numbers in here just to make our lives a little bit better. Okay, did I say F? I just said that, didn't I? I just cursed pretty bad.
No.
It's my passion, okay? So I hope it's coming across as passion. Okay, so we were sitting there and we just had t squared and we were like, we're just gonna keep on doing integration by parts and just knock that t squared down to a 1, right? Okay, so if we let that be u, no matter how many times we do integration, it's never going away. Do you all agree?
Yes.
Because the derivative of e to the 2x is gonna continue to be e to the 2x, no matter how many times we do it. But you could also say the same thing for the cosine 5x. No matter how many times you do integration by parts, it's just going to keep cycling back between sine and cosine.
Mm-hmm.
So this problem gives you some appearance that there's just like no way you can get it. Like it won't work, but it does, all right? And you got to see it though. You got to see it happen, all right? That's why I was saying there's not a cookie cutter way. Like if we see a power out here, like x to the 5th power, then yeah, you can say, I'm gonna just chip that down. 5 iterations of integration by parts. But this one, nope, not happening. So we take a swing, right? You step up to the plate and you pick. So I'm gonna pick for us. I'm gonna go with e to the 2x. It actually turns out that you could do it. This is an example of a problem where you could actually have done it either way. It doesn't matter how you pick the u, it'll work both ways. But there's no way to know that right now. Like you wouldn't be able to know that unless you've had the experience of this problem. I'm going to put a star next to this. This is a classic problem. Okay, this is a problem that all Cal 2 students have to experience, and a problem that I enjoy putting on tests. I enjoy it because I know you're going to enjoy it. All right, here we go. Derivative time. So du is 2e to the e to the 2x dx. That's chain rule, right? That 2 pops out.
Mm-hmm.
Okay, v, I've got to take the antiderivative. So 1/5, I have to scale it, sine 5x. There's my ultraviolet. There's my voodoo. So I say that this equals e, let me do the 1/5 e to the 2x sine 5x. We got to get moving on this problem. Minus a little bit of a space in the front. What constant can come out here?
1/5.
1/5 and
2.
So I'm going to put 2
So
over 5.
1/5.
Then
2/5.
e to the 2x sine of 5x dx. So when I'm putting the voodoo together, I just chose to put the e to the 2x in front of the sine of 5x. You could have switched the order. It doesn't matter. I'm just trying to say consistent within the problems. Okay, so we look at that new integral. Nothing got better, right? Nothing got better. We still have e to the 2x, and now we've got a sine instead of a cosine. So we've achieved nothing, it seems. Okay, but we're going to go again. And you're like, why are we wasting our time? Nothing got better. Trust me, it's going to work. So I chose u to be, again, e to the 2x. I do du, and I get 2e to the 2x dx. And my v is negative 1/5 cosine 5x. I'll give you a moment to write that down. While you're writing that, do you have any questions on this part so far?
Why do we keep writing dx when we're taking the derivative? It's just like the basic?
No, it's because of this. If I let u be equal to e to the 2x, then I'm doing du dx equals e to the 2x times 2, and then I'm multiplying both sides by dx, so that du is equal to this, and that's that.
Oh, okay.
That make sense?
Yes.
All right. Think I'm ready. Oops. What, my video? Come on, stop. There we go, I'm back. All right, so my new universe is right here. That's my new universe, right? That was the one I did this stuff on over here.
Yeah.
So the new integral will be ultraviolet
minus
ultraviolet. Hold on, I'm not done with the violet. Minus a little bit of a space. So I just did this times this, and now I'm going to do this part right here. So can we pull a constant out of the voodoo part?
Yes, the same.
Negative 2/5.
Negative 2/5. And then inside I have what? E to the 2x times cosine 5x dx. On what?
Yeah.
And just keep in mind here that these two can come together, and that'll become a plus 2/5, right?
Mm-hmm.
Okay. So now we look at this new integral, and when we look at that new integral, we should get very frustrated, right? Because that new integral is exactly the original problem. So we've done all this work, and here's the new integral, right?
They cancel
And
out.
here's the original one. But watch, this is freaking beautiful. Watch. This equals, so now I'm going to put it all together. This right here is 1/5 e to the 2x sine 5x. Okay, minus 2/5. And now a bracket, and now all the purple stuff, everything I just got here is going in. So we have negative 1/5 e to the 2x cosine 5x plus 2/5 integral e to the 2x cosine 5x dx, close the bracket. Damn it, I'm running out of time. Okay. Everyone okay with that? I'm about to distribute this through on the next line. All right? But watch what I do. I'm going to write down the original problem. The original problem was e to the 2x cosine 5x dx. And what we've said is that it turns out to be 1/5 e to the 2x sine 5x, and now distribute. plus 2/25, that's that first multiplication through there, e to the 2x cosine 5x. Distribute again, here to here, minus 4/25 times the integral of e to the 2x cosine 5x dx. Does anybody see it? It's hard to see. I mean,
No, so the e to the 2x cosine x is the original.
yeah, so here was the original problem, right? And what we figured out is that that is equal to, right? It is equal to this, right? But I mean, we can't say that, I mean, we can't have the original problem in our answer also. We, you know, it can't be on both sides. Like, it's like solving for x and then having x on the other side of the equation too. It's like, ready? I don't have enough time to let y'all really think about it. Watch this.
It's just
So it's an equation, right? So I'm adding that integral to both sides. Now I'm not adding the whole integral, I'm adding 4/25 of the integral to cancel out on the right-hand side. Do you see how that cancels? On the left-hand side, when you take one of these integrals and you add to it 4/25 of an integral, how many integrals would you have? So it's like add one apple to 4/25 of an apple. How many apples do you have?
29/25.
29/25. So you're just adding the coefficients. So you have 29/25 integrals. This should seem very, very not good. But not that it's not good, but you should just be like, what in the world just happened? One more step. Multiply both sides by 25/29. That would make this a 1, wouldn't it? On the left, and that would give you that integral, which is what we were looking for. So I'd have to distribute this through here and here. If you don't mind, I'd like to finish it up. I get 5/29 e to the 2x sine 5x. And when I distribute there, I get plus 2/29 e to the 2x cosine of 5x. That's our answer. We have to remember to put plus c though. Okay, I'm out of time. Your test is on Tuesday. It's going to cover everything I talked. Did I talk about that last time or no? How many problems, all that?
No.
Okay, y'all have 2 minutes. Can y'all spare 2 minutes? Okay, let me see if I can open this. Okay, just pay attention because I'm going to say things. I'm not going to just tell you what the exam is because I haven't made the exam, but I have an old exam that I can kind of share with you. So in the past, I've given an exam. It was 10 questions. The first question was 2 parts, and it involved taking derivatives of inverse trig functions, inverse hyperbolic functions, using chain rule. So like, you know, what's the derivative of arc sine of this, right? So you have to be able to use the formula along with some chain rule. Maybe there's product rule in there. So problem number 1 is a little bit of differentiation. Problem number 2, and again, this is not your test. I'm just giving you an example of what I've given in the past. Problem number 2, I gave them the acceleration function, and then I gave them 2 pieces of information, asked them to go back and find the position function. So that's something that you did in your homework. After that, we get to integrals. The rest of the problems are integrals. Number 3 is just a power rule problem. Number 4 is a basic U substitution. Number 5 is basic U substitution. Number 6 is basic U substitution. Number 7 is basic U substitution. 8 is substitution. So lots of substitution there. Numbers 9 and number 10 were integration by parts. So let's do a quick poll. Do you want integration by parts on this test or not? I don't mind not giving it, but then it's going to be on the next one. So, and if I did an integration by parts, it would be just some of the easier ones, like where you just do it one time. I wouldn't do it where you have to do it more than one time. So I could give you like 2 integration by parts problems on the test that would be somewhat easy.
Okay.
Not like the one I just did. Okay, the one I just did would not be on the test.
Oh, is
That
there
would
any
be-
credit on the test or?
But it'll be on the final test?
That'll be what?
It'll be on the final test then?
No, it'll be on the next test. Test 2.
No, the third problem, the one you just did, the harder one.
That harder one would be on the next test, not the one, test 2, not test 1.
Okay.
Okay.
As far as answering on our tests, how complex do you want us to go as far as simplification goes?
I'm not concerned about simplification as much as I am about you doing it correctly.
Okay, cool. Thank you.
Yeah.
And how
I know
many
a lot
questions
of
is that again, sir? Did you say 10 questions?
I would expect about 10 questions.
Okay.
I know a lot of professors are really different on this, but do you mind using pen or would you rather pencil?
Personally, I don't like pen unless you're not making any mistakes. But if your final version of what you turn in is nice and clean and it's pen, that's fine. But you're going to make copies of it anyway, right? Like you're going to take pictures. So I'm not going to see it, but neatness will matter to me. I do want to be able to read your work. So what you should expect, I'm so sorry I went over on time here. What you should expect is we come in on Tuesday, everyone comes to class, and then what I'm going to do is I'm going to send everyone the exam through Canvas, and I'm also going to send it through the chat room here. Once you get the exam, I'm going to give everyone 10 minutes to write down the problems.
Okay.
Okay, you're going to all write down the problems. And then you will not be able to have your computer on, but you must have a camera that's on you. And I talked about this a little bit in the orientation, that if you need to use your cell phone as your camera, then log into Zoom, you know, through your app, through an app on the cell phone, and then set up your phone, you know, where I can see your work area. And what I want is to be able to see
the surroundings in ourselves too.
yes, the surroundings in yourself. And so I have it on our main page. I'm opening it right now.
Oh, you have to reshare your screen.
Yeah, I know. Hold on.
Yeah.
I'm getting to it first.
We're allowed to use the reference sheet, right?
You're allowed to have all that stuff. Yes, reference sheets. What? I thought it was on here. Did I go to the wrong semester? There it is. Okay, so there's a picture that I see how, now of course your computer screens won't be on, but you see how you can see me and you can see my desk and you can see what's in front of me. So like right now, my camera, the way it is right now, would not be okay. Because even though you could see me writing here, you can't see what I'm looking at. So I could have like all sorts of stuff taped up in front of me, right? All these problems worked out. And so I'm just trying to keep it fair to everyone. I don't want to have one person who's sitting there and got all these things and other people are trying to take the test, you know, legitimately. I think this first test will be a little bumpy as far as getting things set up, but you know, every test after that, we'll have it kind of done. Any questions?
Sir, can I use does it have to be the phone, or could I have my laptop?
You can use your laptop, that's fine. I'm just suggesting that if your laptop can't move it around, if you have a desktop that can't move around, you just need to be able to position whatever camera you have in a way that I can see your workspace.
Okay.
Do you
Okay.
want to be able to see like our desktop and our paper?
I don't need to be able to like read your paper. I mean,
Yeah.
quite literally, I just need what you see there in that picture, just where you can see me working on something and that I don't have a bunch of stuff around me that I shouldn't have. And I'm not picking up a book, or I'm not going to Wolfram Alpha to go find, you know, the antiderivative of something, you know, like just again, trying to make a level playing field for everyone, okay? You know, if this test were about, can you use a computer to solve the problem, then I would make the test very hard. I'd make it in a way that you can't, the computer wouldn't help you, you know? So we're just level playing field is what we're looking for here.
Okay, cool.
And well, calculators are allowed, right?
Calculators are allowed, but I'm going to be looking at your work, right? So your
Yeah.
work is going to be the most important thing.
Okay.
And formula sheets, right? They're
Yeah.
allowed? Okay.
Yeah. So you'll be basically at the beginning of the test, you'll be quickly holding up your formula sheets to your camera and just kind of flipping through them just so I can see that everyone's got just formula sheets. All right.
The office hours that you have posted there on the syllabus, are those accurate?
Yeah. Have you showed up and I'm not there or something?
No. I'm just, in case I have to show up on like Monday for any questions or anything,
Yeah.
I just want to make sure.
Monday.
Now, as far as the microphone, should we have it all on
No, we'll be
during the
muted.
test?
Everyone will be muted.
Okay.
Yeah, we'll be muted. Yeah, just the video is all I need. Yeah, Monday, my office hours are from 10 to 11 and then from 1 to 2. And then Tuesday, Thursday, before our class from 11 to 12:30.
Okay, cool. Thank you.
Yeah. Mhm.
The work we did today, is that parts by integration, or is that the 6 point?
No, 6.1 is integration by parts. That's what we started doing today.
Did we just do sub and IBP then?
So U sub was 5.5, which we did last time. Are you looking at the
homework sheet? The one where it's like 1 through 7?
this right here?
Yes.
Okay, yeah, so this is a good guide. This test, I'm going to give you problems on integration by parts, IBP, okay? If you look at just the first 7 problems off of that page out of the book, the ebook, that's the level of the problem I'll give you on the test. Now, if you look, I continue later on after this exam, we continue and we do just all 32 problems, and then there's more. So there's still a lot to do in integration by parts. We've just started, well, we've gotten through a pretty good, I've shown you some pretty good ones, but there's some more that we need to see. Does that answer your question, CJ?
Yes, it does. Thank you.
Okay. All right, well, I don't want to keep you any longer. Any other questions?
They go buy a webcam with a long cable.
What do you have? Do you have a desktop right there?
No, this is my laptop.
You can use your laptop. That's fine.
I can't. Well, I can move it, but
You can't move your laptop?
well, I can. But the way I have it, like strung up on my desk and stuff like that, it's
Yeah. Well,
Can't you
I don't want
get
you to have to go buy.
Camera from the school.
We can make it work. I mean, just, you know,
well, I don't
do
want to use
what
my
you
phone.
can. Do what you can.
I don't trust things. I don't trust Zoom.
Trust what?
I don't trust Zoom.
Oh, Zoom. Okay. All right. We good? Okay.
Yeah.
You have a good weekend.
All right. I'll be
Thank you.
around
Take
if
care.
you need me. Okay. Take
Have
care.
a great weekend, sir.
Too.
Thank you.
Thanks.